Well, hello again everybody. Now today we're going to be doing something a little bit different. I've actually brought a piece of equipment home from work. This was sent back to us by one of our customers. For me it was quite interesting to get one of these back because if I look at the date code on it, this is one of the first boards that I ever worked on, and the date code on it goes back to 2001. So we've actually got some thousands of these boards out there in the world, actually installed all around the world in various places, and this product has been incredibly reliable. I think I would say that we probably get, you know, 1 or 2 boards back per year. In fact, probably some years goes by where we don't get a single return for repair. The reason I've brought this home to repair is it's pretty much impossible to repair these at work. We don't really do any electronics in-house anymore, unfortunately. It's all subcontracted out, all the manufacturing. It's actually all subcontracted just locally to Sheffield. But actually to try to get somebody to even look at one of these old boards where, you know, we've got leaded solder and stuff like that, you just can't do it. And I think the reality is I'm just going to repair this board for a favour. It's just that general problem of obsolescence. As I said, the date code for this goes back to 2001. It's all through-hole components. It's using leaded solder. I don't know if you can see the shine on the board. I don't know if it's coming out on camera. Let me show you. Hopefully that's focused in. Can you see that the board looks probably a bit reflective? I think you can see it reflecting the light. Well, this board was actually dipped. It would have been dropped in a vat of conformal coating, because again, the atmosphere that this equipment goes in, it can be hot, it can be cold, it's often damp. Some of it's inside, some of it's outside. So when we designed these boards all these years ago, we were conscious of that. So everything gets conformally coated. But one of the problems with the conformal coating is that it's a little bit nasty to solder through. If you don't clean it off, it kind of corrupts the joint, and you know, it's very smoky and it's not very pleasant. So we've got the letter from the customer here. Let's just have a quick look at that. So he says, we've returning 2 circuit boards to you which have known faults, board 1 and board 2. Board 1 is saying that basically one of the outputs was constantly activated, and they think that well, they said here they've changed out the relay, which I'm guessing is this one because it hasn't got the conformal coating on it. They swapped out the relay, and he says, I tried to desolder the relay, you can see the new one's in place, but whilst desoldering the centre pin, it lifted a bit of track with it. And he says, I thought at worst the LED wouldn't work, but when we reconnected, it didn't work properly. So there's little LED back there. I can't actually remember what the circuit diagram is for this board, but I'm pretty sure that from memory, that the relay coil is in series with the LED. The date on these does go back to 2001, so forgive me if I don't remember in detail how some of these things work. So I can just imagine them probably trying to repair these boards. They were probably using one of those ancient old Weller soldering irons, or probably even worse, one of those gas Weller soldering irons or something like that, and using some unknown solder and flux. But yeah, they're not easy to work on, these boards, because as I say, the joints get contaminated with the conformal coating. And the other problem is, I don't think it's necessarily one of those hindsight things. The actual holes, these are through hole components, and again, just one of the things that you will find is that the holes for all these components are probably, you know, on the tight side. So I'm not surprised they've had a bit of a problem. When they tried to remove the old relay, they would have pulled it out, and the tracks on the top side of the board, they probably just ragged the track off, and I'm not surprised. It's easy to do. Now, if you're going to do this again, and you know that the circuit board is very tight, and you know that you don't have to reuse the component that you're removing. I'm not going to do it on this board because this relay is good, it's a new one. But if the people watching this are ever going to do this repair again, maybe on one of the other boards, what I would actually probably do is, sorry, if I can zoom out a bit. What I would probably do is, if I had a component that I needed to remove, one of these chips for example, or maybe even this relay, in the case of one of these chips I would actually get a pair of fine side cutters in, and I would cut the chip off. I would cut it away from the top, and then I would remove it one pin at a time. And probably the same for this relay. It can be very difficult to get these relays out. So again, what I would probably do if I was to replace this relay, I'd probably get a pair of side cutters or mole grips, and I would destroy the relay. I would just grab hold of it, I would crunch it up, mash it up, and then I would basically break it up to a point where I can have access to the individual pins, and I would just desolder each pin at a time and remove it. And you've got much less chance there of dragging a track off. So I think what I'd like to have a go at first is just seeing if this board does function. Yeah, it's actually quite interesting to get one of these old boards back, you know, just to see how you did. I'm quite pleased to see you know, how long these boards have lasted. I don't think this one has been in service since 2001, because from memory the 2001 date was the first revision of the board. This is actually, I think, got a D code on it, which to me from memory means it's one of the later boards that we produced. There is actually a replacement out for this board, a replacement product, which really is quite different. It uses you know, totally different surface mount technology, as opposed to all this through-hole stuff that's got in here. But it's also amazing just to think how the technology's moved on generally. I mean, what we're going to install here is there's a microprocessor module that goes in here, which is quite a simple, quite a dumb 8-bit microprocessor, and I kind of think back, or look at what we use today, which is you know, an all singing, all dancing ARM chip running at hundreds of megahertz or 100 megahertz or so, whereas you know, this one just probably plods around at, you know, 3 megahertz or something like that. So the you know, the technology's really moved on. Now, at the time when this was brought out, this board would actually replace kind of a huge cabinet filled with PLC type equipment, which is, you know, programmable logic controllers, which are used a lot in automation and stuff like that. But again, back in the day, PLCs were quite big and they weren't particularly powerful or intelligent. And what the clever thing about this board is that this board could talk to lots of other devices on a twisted pair network, which again, from memory, I think it plugs into there, the twisted pair cable. So this board, rather than, again, the old PLC technology, which is still used by some people today, they have a big PLC, a big central controller, and then they have all these different devices around the factory with hundreds and hundreds of wires running backwards and forwards. And yeah, I mean, that's one way of doing it, but it's very expensive to put all that cabling in. And two, from the point of view of faults, well, you get one bad cable in all them hundreds of cables and everything stops working. But the fact you've only got 2 cables as opposed to 600 actually means it makes the whole system much more reliable and much more fault tolerant. But again, back in the day, if you wanted to make devices talk to each other, you were using quite end PLCs. I mean, I seem to think one of the ones I used to use a lot was the an Allen Bradley SLC 500, and you were having to buy the PLC, which was relatively expensive, and then you had to buy something called a scanner card, which would allow the PLC to talk to another PLC or another piece of equipment. And by the time you'd done this, that piece of equipment wasn't very good and it was costing you thousands of pounds. So what we decided to do is, rather than keep using PLCs, we decided to make the investment of doing our own electronics and our own network system, which is what we did. It was very expensive in terms of development, but once we'd done that development, we could actually make hundreds of these boards and supply them all around the world, which we did. So this has been a, you know, somewhat of a workhorse. It was a good investment. So here's one of the microprocessors that we use, and I talked about the network. Well, we use something called Longworks network, and this little black blob here is the it says Etchel on it, FT 10A. That's a free topology twisted pair network, and the free topology bit means that you don't necessarily need terminators. You can wire devices in parallel with each other. You can have long lengths of wire or short stubs. You can wire equipment in groups, or you can wire it in a bus configuration. So basically it just means you have freedom to connect up your network in a variety of different ways, and it does work, works very well. The network is quite slow, but it's very reliable and it's very deterministic, and it's got a lot of inbuilt error checking as well. But on here you've got, you know, pretty much a pretty dim 8-bit microprocessor, a little bit of memory, and the other thing that this device had, again from memory, it has a serial port on it. And you know, I can't even remember what we used the serial port for now. That's how long ago it is. But we need, for some reason I think we needed the serial port. Ah no, it wasn't that. This device had some extended memory on it. We needed more memory, and it just so happens that the module that came with the extended memory also came with the serial port on. This board, sorry, is not something that we make. We bought this board in, and again, this is an obsolete part. This part was made by CNS, which is Control Network Solutions, and again, we've used thousands of these, and historically they've been very reliable. In fact, I don't know if I've ever replaced a single one of them. Anyway, we've got to just pop this in here. That's the biggest problem here, that what you don't want to do is install it correctly and get some of the pins one slot out, because that can cause problems. Right, I'm just making sure that there's no metal filings on here, because I'm going to power this up, and some of this board, it is going to be live. Everything at this end of the board is potentially live, but everything on this side is 24 volt DC. So we've got the mains power supply comes in here. We've got a Schaffner filter there, EMC filter. We've got some fusing. We've got a power indicator there, and we've also got some mains fail detection here, which fires an interrupt on the microprocessor, so we know if the mains has failed. We've got a step-down transformer from memory, 230 to 24 volts. I think we go down to 24 volts, and off one of those sides of the transformers we've got a DC to DC converter, which takes us to 5 volts. And no, it's none of this 3.3 volt rubbish. It's proper man's TTL logic here. 5 volt logic, perfect. Don't know why anybody wants that 3 volt rubbish. All this I/O, it is controlled by the microprocessor here. It talks on an I2C bus, because there isn't enough pins on this chip to control all the various inputs and outputs. And again, I'm acting from memory here, because I can't remember. I just can't remember in detail how it works now. It's a long time ago. It's 18 years ago we designed this. You've got I2C squirting out of the chip, and you've got some I2C expander logic here that converts I2C into parallel input-output. And I can't remember if the devices are dual, if they're a specific input or output devices, or if they do both input and output. This side of the board here is the inputs. All the inputs are up to isolated. From memory, all the inputs are 110 volt AC. We did also do a 24 volt version of the board, and I can't remember if this is 110 or 24. I suspect it could be 110 because of the size of these resistors here. So again, all the inputs are up to isolated, and then we've got all the outputs here, all the relay outputs, and these relays are Omron 5 amp relays. We've had some optional stubber networks here. You can see here there's some components not fitted. Well, they're to fit some capacitors and resistors for snubbing the changeover contacts on the relay, but we never actually ended up fitting any of those. We really designed those for when we were switching inductive loads, but as it happened we never really connected anything particularly inductive to these boards in the end, so we didn't bother fitting them. And we actually sent the board to do all the EMC compliance testing without these fitted, so we did it without them. So there's no need to fit them when we went into production, but they were put there as a bit of you know, added protection in case we needed them, and we could fit them if we had to. And then we've got a series of MOVs here. So again, I'm working from memory, and I'm pretty sure that all these channels here, this 1, 2, 3, 4, 5, 6, these 6 channels here are all 230 volt outputs. whereas it just happens that we've got two different coloured mobs here. Now they could have been the same colour, they just happen to be a different colour. Well, these are 110 volt mobs, and again they're just designed to take any kick from inductive loads. The loads that we can't control aren't particularly inductive, they're usually just normal lamps. So the other thing I've got to fit here is actually the HMI, you know, the interface board. I don't know whether or not this board will work. Again, this is just a board that I pulled out of our old bits of test kit. This uses one of those LCDs with the you know, the Attache drivers, and it's got those what do you call them little black blobs? I've forgotten those. Was it chip on board or something? There's a name for it, isn't there? These little bits of black goo where they've got the wafer actually bonded to the circuit board. Depending on the age of this board, I know that again over like a 10-year period, we found that one of the boards became obsolete and we had to source something else. Now in theory, the new board was a pin for pin replacement for the old one. But as it turned out, occasionally you would get some corruption on the display because the timing requirements were very, very slightly different between the old LCD display and the new one. So again, we may be lucky and the LCD may work, or we might be unlucky and just find it's a little bit corrupted. So we'll just have to plug it in and try it. Right, here's the exciting bit now. Let's plug it in and switch it on. Alright, yeah, we are slightly unlucky. So, yeah, this is one of the boards which has got the different version. So the version of firmware that we've got on here isn't quite matching my not 7 segment, it's not quite matching my LCD display because some of the characters are good and some of them are corrupted. So, it says press enter, let's press enter. Okay, so basically it seems to have recovered itself. I seem to think it's a little bit of an intermittent issue, but it was fixed for the later versions of the display by a timing tweak in the firmware. But this is a piece of test software, and what this does is it monitors all the inputs and it actually allows us to switch on all the outputs separately. So if I just press 1, in theory relay 1 should energise. So here's input 0, that seems to be working, we can hear the relay click. Now input 1, that's working okay. Input 2, that's working okay. Input 3, yep, that's the one that doesn't work properly. 4, yep, fine. 5, 6 and 7. So what was it? Was it 4? Which one didn't work? Right, input 3. So it's this input that's duff here. Now I think it should be possible to do a little patch wire repair on this without removing the relay and doing a bit more damage, but I'm quite intrigued to see if I can get this relay out, and also I'm going to suck off the old solder because I don't know what the customer has used. As I say, for all I know, he's used plumber's solder. I mean, I'm sure they haven't because they are good guys down there who've returned this board, but I don't know what it is, so I need to put something back on that I know is going to be good. To put my solder sucker on there, and it hasn't melted the solder, which again is something that that happens. I mean, I would have thought this is relatively new solder on here, but old solder, it goes hard. The melting point of old solder actually increases. A lot of people kind of wonder why, and what it is strangely enough, copper, which is what, you know, tracks and legs on components are made out of, copper is actually soluble in tin and lead alloy. So what happens is some of the copper migrates into the solder, which actually raises the melting point. And of course, I'm sure the people that had a go at repairing this don't have one of these tools that I have. So there is a little bit of a knack to doing it when you're using a desoldering tool. What you actually want to do is you want to suck the solder off, and then you want to kind of do a little circular motion, which basically is breaking the relay. Sorry, it's breaking the legs of the device. You just want to break them away from the hole that they go through and make sure you've sucked any solder out of the gaps between them. So, you know, you just do this little wobbly motion, wiggle it around, and you can actually hear the vacuum pulling through. If you can hear the vacuum whistling through the gap between the pins and the holes that they're in, that's really what you want. So this relay is loose now, so very, very gently, and that's pulled it out. What they've done is when they pulled the old relay out, when they pulled it out, what they've done is there's actually a track on this side of the board which is attached to a pad. So what I suspect happened is they didn't quite have enough heat, or they hadn't removed quite all the solder. So when they pulled this relay out, they ripped the pad off, and I think the through-hole plating's gone as well. So unfortunately, this is the coil contact which is wired through this LED here. Yeah, they've pulled the pad off and they've ripped out the through-hole plating. Actually, this relay came out very easily. I must be confusing this with one of the other boards that I've worked on in the past. Yeah, one of the electronics engineers at work, Simon, I've ragged him more than once for telling him, you know, how tight he makes these components. But you know, you can't complain too much because, like I say, if you have to repair one board a year out of the thousands we've got out there, I mean, these things have stood the test of time, haven't they? Anyway, this is a new relay, so we don't need to swap it out. Although I am tempted to put, no, we won't. We'll leave it as it is. I have got some higher capacity relays I could put in there, but we'll leave it as it is, and then it's going back to the customer standard as they delivered it to me. I am just going to double check the coding on it. Have we got the right relay? Yeah, 24 volt DC coil. Yep, that's fine. So what I'm going to do, I'm just going to set up my little microscope camera because this camera that you're looking at now won't focus in. So we'll set that up just so you can have a look. Now, I'm sorry to say I made the cardinal sin there of not switching the record function on the microscope. So I've just done quite a bit of filming and not shown it yet, so that's a bit annoying. The pad had lifted off here. What would have happened is when they pulled the old relay off, the top of the pad would still have been stuck to the bottom of the pin, the bottom of the leg of the relay, and this is one of the coil pins, and it would have, when they just pulled the old relay out with it still soldered to it, it would have just ripped the pad off, and it did leave some of the track here kind of blowing in the wind, and I've just taken a knife here and I've just trimmed it back because I didn't like the idea of it somehow coming loose later and ending up in the way. So what I'm going to do now is I'm actually just going to get a little blob of actual just clear nail varnish, and I'm going to put a blob on there just to glue the remains of that track down and stop it floating around. I do like to quite use a little bit of this clear nail varnish. It's pretty useful for this kind of job. I think the main reasons it's useful is it just acts as a little bit of an adhesive. I mean, it's not a great adhesive, but if you can just get some to flow under the track and then push it back down. The thing about the nail varnish polish, it dries relatively quickly. You can just blow on it and the solvent, the acetone, whatever it uses, does evaporate relatively quickly. Now the way that we're going to repair this is we can actually just turn the board over, and the pad that was missing, or the track that's missing, it goes from the cathode side of this LED onto one of the coil connections. So because the LED is a through-hole component and our relays also through hole, we can actually get at the connection on the back of the board. So one way of doing it would be actually to solder a piece of link wire on the top of the board here, but we'd have trouble getting at it with a soldering iron and stuff like that. I mean, you could do it. You'd probably take a fine piece of wire, you'd solder it on there, push it through the hole, and then solder it on the other side, especially if you wanted to reinstate the through hole plating. But we don't need to do that for here. It's just a single connection, and the through hole plating isn't very important. So what we'll do is we'll run a connection on the back of the board between the LED cathode and the pen. So let's do that now. And just put a little bit of this, again, nail varnish on, just to stop this lead blowing in the wind. And I'll just put a blob to kind of replace the conformal coating that we've might have just washed away there. So there's relay 0 working, 0, 1, 2, and here's our defective one, 3, 4, 5, and 6. So all good. So there's one down.